The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I have the pleasure to introduce my colleague and friend, Mr. John Crawford. Mr. John Crawford is a licensed professional engineer. He has over 50 years of experience in this field, and I said that right, 50 years of experience. So you're talking to a luminary in the field, if you will. He's authored over 520 papers and 400 reports on blast and impact-resistant design. He's the holder of 4 patents on blast and impact-resistant technologies, and I'm interested to hear what he's going to say today on FRP catcher systems. So, John.
Hello. What I'm going to talk about now is considerably different from what you just saw, and it has to do with the level of the loading. And one thing about doing this for 50 years, a lot of things I've seen. Here's a building I was working on some 20 years ago, and the threats for these buildings are at maybe a 1,000-pound bomb at 8 feet, and that gives you a loading of maybe 1, 2,000, 3,000 psi. And you have to contrast that to some of the stuff you just saw, which was in a shock tube, which is like 40 psi. And at 40 psi, you can think about single-degree freedom models and making it a structural system. But at 1,000 and 2,000 psi, you really have a struggle to make it a structural system. And well, we could do it, but the real issue there is the restrictions. Like in this building, the only thing you could do is put something on the inside. It has to be covered up because nobody wants to know you've done anything. And so you have to come up with systems that are going to work in that light. And this wasn't the only building I was doing at the time. It was in the same kind of situation. So what you want to do is recognize that in this building, if all those walls disappeared, the structural system is still going to remain intact. So it's not about the structure, it's only about the infill walls. And if we prevented that debris from those infill walls moving into the building, that would constitute the level of protection that is appropriate for this kind of threat. So this got me into thinking about developing what I call catcher systems. And there we're using FRP mainly that is unbonded to the masonry and is there primarily to capture the debris and hold it at the wall line. And when you start, well, we aren't going to see too much of the test data because there's too many slides here, but if you start looking at the test data, you can see post-test that these bricks and CMU are just pulverized, and there's just nothing there to talk about in terms of a structure. So this is the Marriott in Pakistan. There's many examples of this kind of thing, and when you start looking at the infill walls, they pretty much been blown out by the bomb, and the bomb in this case is considerable distance away even, but it was a large bomb. So you're working in an environment where you kind of expect these things to be severely damaged, and to think about spending the money or even doing a new design so that it wouldn't be happening is probably not a very good way to spend your money. Some years ago, well, quite a few years ago now, we built this building in White Sands to test walls and columns and things like that, and you can see the bomb is right here. So it's a fairly close standoff replicating a car bomb. And then if we look at, so if you, this is post-test, but here's the debris. So the wall is, debris is shoved into the building, and some of the debris actually went out the back side. So there's a lot of velocity on this debris. It's all the way up and down the building. So the issue, even though we actually blew out the column, it really didn't matter. The structure's fine. We just actually pulled the column out and replaced it and then went on and doing more testing. But when you saw that picture, and that was in about 98, it was like, well, we need to pay a lot more attention to walls and how to protect people from that kind of debris. So lots of tests have gone on. people don't talk too much about the tests that went on in those eras, but there's an awful lot of brick and wall tests that were done, especially at Immertech. That data is probably available someplace. I'll just skip through these and try to get to the pictures. So these catcher systems evolved in a couple of different ways. One was to just put an FRP panel behind the masonry. We could attach it. It doesn't really matter too much, but the point is that you're really anchoring it to the diaphragms. And we'll see in a minute when we start looking at these responses that that's quite effective. Now, the worry down here is that at this anchorage is that, these are thin panels and you worry about tearing. And especially early on, there's a real sharp shock front that's in the masonry. We'll see some of that in the calculations. So what we did is add crushable foam between the panel and the masonry to kind of cushion the interaction between the two. This is not a weak crushable foam. We use up to 5,000 psi crushable foams, but usually it's about 400 psi. And the idea is let that distribute the load evenly down at the support. It's mostly about protecting the supports and the interaction between the support and the FRP. So here's a good example of one of the FRPs that we're using. This is a Kevlar, what's called a Kevlar laminate that was produced by DuPont for tornado shelters. And this particular brand is 6 layers, and you get about 12,000 psi per inch strength, which is plenty of strength for these kinds of applications. Now, Kevlar doesn't have much in the way of ductility, but you pick up ductility by the way you design these attachments. So you can design the attachments to have a lot of give, which in essence provides an elastic kind of quasi-plastic response to the Kevlar. At least that's what it looks like from the system viewpoint. So, key features here is almost all the jobs that I've been involved in involved very high blast loads. Recognize right from the get-go that the structural system in terms of the masonry is just not going to be there. And the other nice thing about this system is it's very easy to predict the loads in the system. It's very easy to do the design. I'm going to show you the design tools for that, very simple design tools. And it makes just for a much easier design. The problem with the single graffiti model in this regard is you're really struggling to figure out the resistance function. And especially when you start looking at the real boundary conditions for masonry walls. Often the masonry wall at the top of it is just dry packed and it's really not even hardly attached. And at the bottom it's not much more attached. So it's hard to, if you have to think about the boundary conditions, it's hard to really get to what they might be. So here's a little schematic of the system. The pink material here is the foam. Any kind of masonry wall really doesn't matter. I really don't need to know anything about the properties of masonry wall other than the mass. That's all I need to know. And down here you can come up with all sorts of clever anchorages to give you ductility. Right here I'm using a crushable foam and using some Belleville washers on the lead bolts to essentially make sure that I get a ductile response at the anchorage and I get some motion at the anchorage. I really do want it to move up a little bit. It makes a big difference in the if you hard mount it, you get a shock load in the tensile capacity, tensile force in the fabric, and that's what you don't want to be doing that. So, part of the development of this system, spent a lot of time looking at finite element models. This is just one picture of those kinds of responses. What the main thing to note here is that when you look at these systems, what you get in terms of response is what I call a kink wave. In essence, you start off with the system being perfectly flat, and then you develop a kink at the top, and that kink just migrates down here to where you finally end up with something like this. That is a key parameter that you recognize, makes it very easy to do the design procedure. One of the things we did was look at several hundred runs, trying to look at variations of parameters like panel thickness and mass of the wall and anything we could think of. And we were looking at it all across all the parameters in terms of the peak forces and the way the forces looked in the fabric itself. This is the tip. This starts here from the left. This really shows the kink wave very nicely. These little lumps are just the masses of the wall. And this is the FRP line. And in between that, we have a little interaction diagram for the mass interaction to the FRP. So what happens is time zero, there's no deflection, and then this kink wave starts, and the kink wave just gradually moves down, and when it hits bottom, the whole system is at rest. Looking at the forces, typical of a system like that, so you have a relatively simple velocity. It's constant velocity. At the center line, this is the deflection at the center line. Constant velocity until the system bottoms out, and that comes to rest. Over here, if you look at the tension in the FRP, you go initially not much tension, and then it hits a constant pretty much until it comes to rest, and then it goes back to zero. That's very typical of what the stresses look like in the FRP. What is the tricky part in all this stuff is the shear. So the reaction shear force over with the FRP attachment, and what you always have to worry about is the shear shock. So right at the get-go, you have an initial shear shock, which is related to the actual shock front, not to the response of the wall, but to the shock front getting into the system and hitting that support. What happens here is I can bring this down a lot by the way I tailor the foam and the thickness of the foam and a few other things like that. So I can play around with that a lot, but ultimately you have a little bit of this, and the foam helps you get through this, because the shock can't really get to the FRP because the foam's between it and the actual masonry. So you get a little bit of this, but if you have a little ductility in the system right at the anchorage, this isn't going to bother you. And then once we get through this, and we're talking, about 200 or 300 microseconds here. So once we get through that, the shear now is related just to the membrane response of the FRP. It's almost a constant value until we bottom out on the deflection, and it goes back to zero. That's kind of the basic setup for these systems, and you can look at that stuff and come up with a design tool. And that design tool is based on these kinds of assumptions. The sheet is composed of a bilinear material, and if we're using FRP, the bilinearness, or the plasticity part of that, we get with the anchorage. There is a little plasticity in Kevlar, but we're not so much looking at that as letting the anchorage do it. Second assumption, the final deformed shape, may be represented by a triangle form, is basically this essentially the kink wave. When it comes to rest, it's a triangle. Debris generated from the breakup of the masonry, the velocity of that debris we know pretty well. It's the impulse divided by the mass of the wall. And that's shown over and over in tests. In assumption 4, the energy involved in the wall's response and breakup is negligible as compared to the kinetic energy of the debris. And again, you'll see that in all these calculations we do. Yes, the structure gives you a little resistance, but when you do the comparisons at the end of the day, there's so little energy going out into the structural part of that resistance that just you can pretty much ignore it, and you'll see when I show you the comparisons between the design tool and the final model, which incorporates all this structure stiffness, you'll see there isn't that much difference, and it's always upper bound. And then 5 is the strains in the panel are fairly uniform over its area and through its thickness, and you saw that when I showed you the kink wave results for the in-plane tensions, pretty much a constant. So here's what the deformed shape for the FRP is going to look like when the system comes to rest, and you use that in order to calculate the internal strain energy. And over here, if you look, this is all test data from, again, about 20 years ago, but all it tells you is that if you look at the I over M line, or the velocity you calculate for I over M, it lines up quite well with the data. And that is essentially the rigid body velocity. You look at the material, you just assume a bilinear material, and that's all the assumption I need. And once I do that, I can equate the internal strain energy with the kinetic energy of the debris, and calculate, after a little fooling around, the deflection, the maximum deflection, which is essentially the centerline deflection of the FRP, and that's based upon a strain measure which calculates, these are all known parameters at the beginning of the analysis. 5 minutes? Wow, I'm doing pretty good, right? Okay. Well, if I know all that, then I also know the forces in the system, and from that I can calculate all the anchorage properties I need to know about. So here's the force I can calculate based on what I just talked about. I calculate that from the strain, and taking the angle, which I get from the delta max, I can calculate the angle of this. Then if I use, this is using an angle to do the support, but any other thing you're doing, you can calculate whatever you need to do and get the anchorage forces and the bolt forces in the bolt design. So that's sort of the gist of the design method. What's important to note here is you need to know nothing about the structural resistance of the wall. And that's really crucial, because you often don't know much about that, or if you're trying to make that assumption, it's very hard, especially when talking a couple thousand PSI laying up against this thing. So, looking at some validation studies we did, Mark let me show one. So, what we do is full up calculations, and looking at, this happens to be a brick wall, but the idea is looking at these calculations, and we're looking at a catcher system, And then we're comparing the results with the LS-DYNA calculation to essentially the simplified tool. You can see it right over, whoops. No, was that the comparison? Okay, so for LS-DYNA, we got a 21-inch deflection. For the simplified equations, we got a 26-inch deflection. The difference here, the 5 inches, is related to this. It has some structural response properties, so LS-DYNA picks that up and the tool doesn't. But the whole point is it's conservative, and it's certainly simple to use, and you certainly wouldn't want to use that LS-DYNA calc to be doing this kind of thing. And we've done several of those things to show that the tool is pretty good at picking up upper bound results for the design. So a little bit more here in terms of how walls operate. These are some tests that were run at UCSD. And what we're looking at here is a wall that's representative of a control room and a refinery. And the point here is that this wall is sitting just here on the ground. It has some block here to hold it from moving that way. Up at the front, it's another kind of block that's resting against a block, so it's not really very structural. And the idea was to put an FRP on the back side of that as a strengthening measure, and it's bonded in this case. And it really doesn't matter too much if it's bonded. Oh, there's a video here. Okay, you want to do the video again? Doesn't work. Okay. Well, what you would see if you ran the video is you got a nice shear crack down here. And why that's okay is because the FRP is bonded or anchored down here, so it just does as a local catcher system. So even if you're trying to make this quasi-structural, and these are much lower loads, these are like 300 psi milliseconds, where the ones I was showing you before them are like 3,000 psi millisecond loads. The notion of doing the anchorage makes it so that even when I get these shear cracks, I haven't lost the wall. Just for the grins, we went through and did the resistance functions for that kind of wall, and this is the resistance function out of the finite element method. This would be the resistance of the existing wall. And I guess one of the things to note, there's not a whole lot of plasticity once you hit the peak on these things. If we look at the calculation, this is the deformed shape for that resistance function. What's kind of interesting is you're getting the yielding up here at the top. You can see the slide, essentially the block is holding it up here, and it's pretty much held here in place. We're not seeing the shear failure down here, which you actually see in the blast test. So it gives you some notion too about the resistance functions aren't necessarily going to sweep out the rate failure mode. So these are all concerns you have when you work with resistance functions, is how applicable they are to the actual event. So I think that sort of is the end of my talk, and so I guess we'll entertain some questions.
What's the order of magnitude of the out-of-plane deformation for this catcher system, and is there a limit? And if there's a limit, how do you go about reducing that?
It's like 6, 7 inches. You can make it anything you want. You just add more FRP. You remember, it's related to the stiffness of the in-plane forces, but the more FRP you add, the more of those forces you add, the more anchorage you got to come up with. But it's not much. 6, 12 inches is probably pretty acceptable most places, especially for that kind of load. Yeah, I looked at that some years ago too. In a lot of buildings, you can lose 20, 30 feet of wall and still have the load-bearing system work. So the first thing you do is say, how big a breach can I handle without losing the load-bearing system? And if you can handle a pretty big breach, go to a catcher system, because when you've got 3,000 psi on the wall and you're going to make it structural, that's really a challenge. And what it does, it really messes up the building in terms of looks, in terms of the inside. You're going to have to do something on the inside. Probably, usually what they do is they put in another wall that's actually load-bearing just inboard, and you try to protect that wall. So it puts you into a lot of bad choices if you want to start making these structural. It's just a contact surface and friction. So it basically can't take any in-plane load. It's representative of liking a bar joist ceiling. So you really don't have much resistance up there. It just holds it so it doesn't move in. And that's a lot of structures. This is like a control room kind of structure. They're just very weak roofs.
Any more questions? Okay. Is this a reinforced wall?
No, I don't think it is. It's just grouted. I mean, we've looked at all sorts of things, so I don't remember. But I did have the model in here before he took it out, which has no rebar. Yeah. I don't know, quite frankly. If Lauren was here, she would tell me probably. Oh, I don't see her though. I've actually run these tests, and I didn't make the count. No, remember, mass is your friend. The thicker it is, the less energy you got to deal with. So if you've got the 3-foot wall, you probably hardly need anything there. It's really, really kind of a cool way of looking at things. And in fact, what you would think about is if you were doing new construction, throw in another, 3 feet of brick or something. It's going to be helpful. So. Well, that's not my problem. That was the UK, so there's no seismic.
Yeah, time for one more question.
We do an awful lot of different things, but the simple thing to do is where the bolts tie the angle into the diaphragm. Use a crushable washer, like a bevel washer or something. So you get a little upward motion, and maybe the back line you make fixed. You still got to get the FRP attached to things, but it's maybe I glossed over a little too much, but there's a lot of choices you have there, and you can come up with all sorts of things to think about. But it is something if you lose this system, where you're going to lose it's in the Anchorage. But what actually is maybe more important, what we found just in doing our test articles, is making sure the guy building it builds it towards your spec. And that's probably your worst problem, is the guy is going to screw it up every which way he can. And don't use aluminum. That's the other thing. It's way too soft.